Thank you for having me. Thank you guys for being here. My name is Jana Tumova. I'm an assistant professor here in Robotics Perception Learning Department. My background is very much formal methods, but I happen to teach AI. I happen to be looking into formal methods for artificial intelligence, machine learning, just a little bit. So that's what I'm going to be talking about. And Martin gave me an uneasy task. He wrote that he would like me to help you understand the breadth of AI, promises and current limitations of deep learning and reinforcement learning, and some of the trends to combine model-based methods and those using deep learning and reinforcement learning. So that is a topic that could go on for a while, a week or a month. But what I'm going to do today is just brush it over very briefly, shallow, test the waters, and then tomorrow we will dive in. Because I've heard that you have different backgrounds, perhaps you even don't know principles of machine learning and things like that. So let's try. So first thing, I would like you to go to a webpage called www.menti.com. Type in code 737250. And there is a question waiting for you, and that is, what is AI? And I would like you to type in what is your definition of AI? What do you think is AI? Mm-hmm. Everyone's shy. No one's answering yet. Everyone's waiting for the first person to hit the enter button, right? Mm-hmm. Three answers so far.
Are bachelor, master students, or PhD students fasting slower or quicker?
I don't know, that statistics I don't have. So we are getting some really interesting answers here. AI it works, but we cannot reason why. That's an interesting definition. That means that AI is inherently unsafe. Ability to learn from new situations, computer systems that can learn and train itself to learn in new ways, ability to reason, automated deriving or functionality from examples, use of machine learning algorithms for someone is AI. Concept that a machine does a particular job with predefined behavior, input data, complex system, and a situation where a machine demonstrates intelligence in the form of learning. I have also seen modeling human behavior and so on. So there are very many definitions of AI, and each of you is in a way right. So for instance, we cannot really say about the current AI algorithms why they work, but we would like to. So what AI really is, someone wrote programs in Prolog, could be two. So what AI really is, either you can define it as thinking like a human being, acting like a human being, thinking rationally, or acting rationally. Those are the four classical definitions of AI. If you Google it up on the internet, you get multiple different definitions. But if you think about intelligent human being, there is more to it than learning, right? We learn, we do solve problems, we reason, we plan, we make decisions. But a part of AI is also communication and perception. The fact that we can use language, that we speak, that we understand each other, that's also part of AI. Vision is part of AI. And in a way, moving and manipulating objects is a part of our intelligence too. That's sort of embodied intelligence, right? So it's some sort of ability of an artificial machine to do stuff, do abilities that we consider to be exhibitions of intelligence behavior. But what it is also, it is an area of computer science, right? So AI, for me, as a person who uses that algorithms in various ways, is just a collection of powerful techniques. When I say artificial intelligent creature should be able to solve problems, what I have in mind is that it should be able to perform some kind of like search of state space or adversarial search of state space. It projects onto a mathematical technique. When we talk about reasoning, planning decisions, it relates to classical topics in computer science like logic, inference, planning algorithms, and also reinforcement learning. When we say learn, what we typically mean is some sort of machine learning or neural nets, topics like that relate to that ability. Communicate and perceive, that is computer vision, perception, speech recognition and synthesis, natural language processing, move and manipulate objects, robotics. So I don't think that there is in the world one AI researcher who would be doing research in all of these fields of computer science, in all of the AI. Different people focus on different aspects of it, and then we try to put it together to make something that works as artificial intelligence. What is interesting is that today there is no general artificial intelligence. If you think about the current applications, the things that are smart on the outside, the thing that give you the personalized advertisement, the chatbots, the Google Translate, you can see some of the features of the intelligence in them, but not all of them necessarily, right? So that's kind of like intro to AI. If you are interested in the individual algorithms, I can recommend this book. It's called Artificial Intelligence by Russell and Norvig. It's about this thick. And there is not so much about learning in it. It's a lot of other things too. What else is AI? AI is a very hot trend. So I'm not sure if you are familiar with this Gartner hype curve. Who knows Gartner hype curve? Almost everyone knows Gartner hype curve. Cool. So this is a curve of hype or cycles in technology. This is how our expectations about technology growing. Then it suddenly drops into disillusionment. And then there is a slope of enlightenment, and then is plateau of productivity. So we have great expectation of some technology, then we are like, oh, it actually doesn't work, and then we realize, oh, it actually kind of works, and then we are ready to start using it. This is deep neural networks as August 2018. You can see a bunch of other things in this curve. There is edge AI is here. 5G, autonomous driving level 5 is coming up, but it's envisioned in more than 10 years, while autonomous driving level 4 is already behind the expectation curve. We kind of know, we are kind of getting to realize what we can and what we cannot do. There are autonomous mobile robots here and so on. So you see that part of the AI is going up, part of the AI is really up there, and part of the AI is already on its way down. All right, but AI is also not a new thing. AI is a thing that is here since 1956, exactly. That's when it was anchored as a term, artificial intelligence. What you see here is a picture from 1997. You know who is this guy? That's Kasparov. So he is playing against Deep Blue machine. Deep Blue is a chess-playing computer. It's the first computer that defeated master in chess. Funny story, there is nothing about deep learning in Deep Blue, really. It's just a coincidence that is named that way. The techniques that are inside are mostly adversarial search, alpha beta pruning, and lots and lots and lots of smart heuristics. So AI is a lot about heuristics. There is no universal thing that would work for all. So for instance, what you have here in this Deep Blue machine, you wouldn't be able to use it to play any other game. And a similar thing holds for AlphaGo. Have you heard of AlphaGo? You have heard of AlphaGo. That's the Monte Carlo-based program that defeated master in Go for the first time. That's just a few years ago. And it's amazing. Go is a game that has a really large branching factor. So the techniques that were used here are not really usable in there. You cannot just go and explore all the possibilities that are there. It's much larger branching factor than in chess, and that's why they had to use different kind of techniques. So this is more based on Monte Carlo search, but yet I cannot take AlphaGo and let it do any other thing. I cannot make it, predict what you are going to buy tomorrow and offer you advertisement based on that. Okay. So now we have sort of like have a feeling what's AI. I want you to go to the Menti slide again. Not yet, not yet. Now, refresh and tell me how much you know about AI so that I know how to pose this talk. So just choose between how much you know from not at all to I'm a pro on scale from 1 to 5, I think. Okay. We have some specialists in deep learning here, seems like. Okay, very cool. So we are somewhere in knowing a little bit, not knowing, not being a pro. So I assume that you know the basic principles now, generally, and that but you haven't touched it in depth yet. Cool. Then I will adjust to that. So, learning. We are going to talk about learning because that's the thing that is up there now. That is sort of very hot. So, the first dimension of learning is that we have supervised learning with labeled data, we have classification and regression, we have unsupervised learning with unlabeled data, and we have reinforcement learning. That's the three types of learning along one dimension of axis. Raise your hand, or I was told by Martin you need to stand up. So now everyone who doesn't need further explanation of what these things are stands up. Who doesn't need? No, I'm so that they are not ashamed, So who doesn't need explanation? Stand up. Okay, so why did you cross like you are somewhere around 2? Come on. Okay, cool. So I'm going to do extra explanation, and then I'm going to create a question for the other types. So supervised learning. What is meant by supervised learning? You have labeled data, so you know a bunch of inputs that map onto your output. In classification, we are, for instance, looking into application scenarios like I've got a bunch of pictures of these weird spots on my skin, and I have classification, which is cancer, which is not cancer. Right? What I'm trying to learn is that if I give my machine learning algorithm a new picture of a new spot, the algorithm is going to tell me, probably you have cancer, probably you don't have cancer. right? This is one of the applications that people are actually looking into these days, helping doctors to diagnose things. So classification is about putting things into classes based on some set of examples that you know which classes it belong. Another example is cats and dogs, right? I've got a bunch of pictures of cats. I know those are cats. I've got a bunch of pictures of dogs. I know those are dogs. And then I get a new picture and I ask my machine learning algorithm, is it a cat or is it a dog? And the machine learning algorithm tells me, ideally. Regression is really about finding the relationships between inputs and outputs. And sometimes, or typically, we use it, for instance, for prediction. So the very, very typical example would be, I've got a house market, and I know how much houses cost in the neighborhood where I live. I know that my apartment was sold for this amount of money, my neighbor's apartment was sold for this amount of money, and then I give it a new apartment, I say, like, how much should it cost? How much should I ask for it? So this is the finding of the mapping between inputs, the descriptions of the apartments, and outputs, the price. Okay? Right. So that's regression. In unsupervised learning, what we are working with is unlabeled data. What does it mean? That no one told me what is cat, no one told me what is dog. But you are trying to find out what are the classes of similar things, right? So I have an iPhone, and at some point, iPhone started showing me like, this is probably the same person kind of thing. And it kept showing me pictures of my daughter. And I never said, this is my daughter. I never labeled the data. But it looked at the pictures, and there was this kid with blonde hair, and it started finding similarities and clustered all the pictures of my daughter and said, probably this is the same person. This is unsupervised learning, right? And then there's a third class of learning algorithms. And its aim is completely different than these two. And it is about making decisions. So I want to learn what are the optimal decisions that I should be making to do the best I can. That's basically the point of reinforcement learning. Why is it a learning? Because often we do that in unmodeled, unknown environments with a high degree of uncertainty. And often we use it also as a heuristic technique to speed up our search for things when models are too complex. Okay, so that's the first type of classification of machine learning algorithms, supervised, unsupervised reinforcement. Second dimension is deep versus non-deep. So each of these, supervised, unsupervised, and reinforcement, can come up with deep version and non-deep version. Now, what does the deep version mean? So far, so good? Yeah? Should I speed up or slow down? Who wants me to speed up, stands up. Who wants me to slow down, stands up. Who wants me to keep the pace, stands up. Excellent. I made them stand up. Okay, Martin. Good. Deep learning. So, super basic. So this is credit goes to Gary Marcus, who is like this amazing machine learning researcher. Have you seen this picture? So now let's wave hands. Who has seen this picture before? Excellent. So can you interpret it? Do you know what it means? Okay, I'm going to ask differently. What important ingredients are not depicted in the picture and belong to machine learning? Weightings, right? So we are missing the weights that are super important. So just to sum up, what I'm trying to do is transform some input to some output. I've got a bunch of hidden layers. All of these are functions. The inputs go in. There are some weights. and so on. And in the end, this is just a big fat function transferring input to output. That's what it is. That's what deep learning is about. Now, designing it, it's of course not so simple. I need to come up with the right shape of the network, and then I need to train it, meaning that I need to figure out the weights from the data that I have. Now, it's got tons of applications. We've got computer vision. We've got Google Translate, right? Personalized advertising, chatbots, robotics. Everything that you can imagine that comes with a lot of data as examples of the right behavior feels like a suitable thing to be used with deep learning approaches. So, what we talk about a lot is how amazing these deep learning algorithms are. What we talk about a little less is what are their actual limitations. And this is again inspired by Gary Marcus, the wordings in particular. So what are the challenges, where the research is going, what challenges we are trying to mitigate? It is data hungry. You really need a lot of data to make your networks kind of make sense. If you don't, you come up with functions that overfit your data. If you get 10 examples of 10 houses and 10 prices, you're going to have like a function that looks probably like that around the points. You don't want that. You want something that is true. So it is a lot data hungry. Second thing, it's brittle in the sense that there is no contextualization. So one thing that we as people are able to do is when I show my daughter a picture of a dog, like cartoon dog, and then she knows the dog from the street. She makes the association, she knows that's the same kind of dog. And I can train my deep network recognizing dog and dog cartoons. When I show my daughter a cartoon of elephant, and then she sees an elephant in real life, she knows that this is an elephant. Neural nets up to date cannot really do that. There are many efforts to make deep nets transferable. It's called transfer learning, meaning that they should be used for more purposes that they were really designed for. Right? So the universality we are missing, the contextualization. They're sort of shallow. So I said it's just a big fat function that transfers input to output, and that's what it is. It doesn't have any sense of what's inside. It doesn't have any common sense, any real understanding on what's happening. We, people, we have that, right? We are born with some feeling for what makes sense and what doesn't make sense. And the neural nets don't have this kind of sanity check, right? And they're opaque. They're opaque. They are full of these unexplainable black boxes. So a lot of research goes into explainability, explainable machine learning, because we want to know what's happening inside. Why did we get the answer that we got? It's going to give you an answer, but it's not going to tell you how it got to that. We as people are often able to explain ourselves and say how we got to a particular point. But what it makes is that machine learning is something that we have to trust, or we don't trust it, and if we don't trust it, can we use it? And are we going to blindly trust it? That's a question. So all of these challenges are great because researchers love challenges because that gives us space to do some research, all right? So in practice, what these things mean is that even though the stop sign is successfully recognized as stop sign, this is one of the real examples that was not recognized as a stop sign with like very well state-of-the-art neural nets. Small changes make big differences. This is also a true story. This is an original image. Yeah, and it's being recognized as 97% confidence this is temple. And then I'm going to perturb the picture just a little bit. To me, this is still a temple, but the machine learning tells me, algorithm, this is 98%, I'm sure that this is ostrich. And these kind of things are called related to the research in field of adversarial examples, where you are looking for small changes that make big changes, these like butterfly effects. So now we are talking about trustworthy cyber-physical systems. And these algorithms are in cyber-physical systems, right? They are in the cars that are going to drive us around. They're in the robots that are going to fly around. They're in all the cyber-physical systems that have some sort of perception and communication with the world. What do we do? What do we do? That's a question. So, you have been hearing a lot about formal methods, right? Here. Or some of you are even experts in formal methods. Who is an expert in the in the area of formal methods? Like wave the other hand than before. No formal methods experts. Okay, who is like familiar with the formal methods idea? Great. Okay. So should I say what formal methods are about? Maybe a little. So maybe a little, what is formal methods about? Basic idea. To make sure that a system runs as we expect it to run, we have simulation and testing and all these kind of great tools that help us to say, yeah, I'm getting sure that this is going to be okay. Formal verification and formal methods, they were designed to give you a proof that something works as expected, or a counterexample that something does not work as expected. So a lot of formal methods are model-based. You take a model of a system, you take some kind of specification that you want the system to satisfy, you somehow put it together, and then you are trying to use mathematical tools to get some kind of proofs. So model checking is essentially exhaustive search in a smart way. Theorem proving is logical inference that brings you from towards some kind of conclusion about the correctness of your system. So formal methods community thought that's a good idea to apply to these deep nets because it's gonna give me some sort of guarantees on how they work. And the truth is that past 2, 3, 4 years, formal methods for machine learning, formal methods of machine learning, and formal methods of machine learning in the loop systems is a big topic. If you go to CPS Week, there is going to be a special track on that. It was not like that 5 years ago. So the trigger in the research in machine learning also triggered research in formal methods. So formal verification or falsification of deepness. Falsification is the opposite thing to verification. That's where you're systematically trying to break it. Systematically trying to show that this is not correct. That's one thing. There's, for instance, an algorithm called ReLuPlex. There's also work by Oxford University by Marta Kwiatkowska, who is the author of PRISM, the classical verification tool. And now I hope no one's listening because a lot of people who are working are going to get offended that I did not mention their names. But that's one approach. I'm going to take a look at the deep net and I'm going to try to prove things about the function that it is, right? Second thing is that let's take a look at end-to-end formal verification or falsification of systems that have deep nets. So I'm not going to take a look at the deep net, but I'm going to take a look at the whole system that has the deep net inside it. And the difference is that if I have a system that is well designed and robust to failures of the deep net, then it still can be okay. My deep net doesn't have to work perfectly as long as the system is able to compensate for that. So this is a little bit different question in nature. And also this community is looking a little bit into formalizing robustness. So the thing that I mentioned with our adversarial example. So how dangerous or how good these deep nets are can be also evaluated based on which adversarial examples it is robust to.
Yeah,
Martin.
Yeah. So in the past days we talked about continuous time systems.
Yeah.
We talked about discrete systems, state machines.
Yeah.
And their combination.
Uh-huh.
As hybrid systems.
As hybrid systems.
But I guess one can clarify here and say that these terms stem more from the discrete side, but they are also being applied
Yes.
for hybrid systems.
Yes, yes, for sure. So traditionally, it's a discrete thing, but hybrid systems, what we do with them, and continuous time and dynamical system, what we do with them is, first of all, we create some kind of discrete abstraction, and that is over-approximating the system behavior. So I'm sure that whatever holds for the discrete abstraction actually holds for the original continuous system too. So we have ways to work with them. Thank you, Martin. Yeah. Okay, an example. This is credit go to Sanchit Seshia. I like this work a lot. It's one of those end-to-end kind of machine learning in the loop efforts. So I've got an autonomous car. There is a learning-based perception going on. Then I'm controlling the car. I've got a real plan that is implemented in the environment and so on. So I've got a loop. And now what they're asking about is through this signal temporal logic formula that says I want to make sure that the distance from my vehicle, from the thing that I'm controlling, to any obstacle in the environment, to any object in the environment, is always larger than delta, right? And then what they basically do in a very high level terms is they explore, they make an assumption that this deep net is always returning the right input, and they explore for where does the controller work well. And then they explore, then they assume that this one is always giving this one always fails, this one is always giving wrong output. And then they again explore when their controller works. And the difference between when the controller works when your perception is perfect and when your controller works in case the perception is absolutely crap gives you exactly the area that is dependent on the quality of your perception system. That's kind of interesting. Okay, how are you doing? All good? All good. Shifting gears. So that was machine learning. Do you have any questions about machine learning and application of formal methods to machine learning kind of things?
Which benefit I gain if I assume that it's wrong anyway and I design a system that it's robust against it, because then I actually don't need it at all.
Yeah, but then, you know,
Just repeat the question.
Oh, I need to repeat. So what's the benefit of assuming that the deep net is completely wrong if I design a controller that is going to be robust to that, right?
I mean, yeah, the controller has to be robust, but yeah, if I say, yeah, my system is robust because it catches any wrong answer anyway, then I can use any other system there as well, then I don't need AI in that case, right?
Yeah, you wouldn't. But you are never going to be able to design such a controller for all possible input and all environmental conditions. Yeah, that's the answer. So if I try not to use perception, I might be able to stay safe in particular conditions, very restrictive conditions, right? In most of the cases, I need to know something to be able to react to that. So giving up perception leads to overly conservative results. If I say I'm not going to see anything, I'm not going to hear anything, I'm just going to go and I want to stay safe, then you are probably going to say me, stay at home. Yeah. Yes?
Then the problem might be, how does the controller know the neural network is getting craps?
Yeah, you just basically make the assumption. Oh yeah, I need to repeat the question. So how do we know that how does my controller know that the machine, that the neural net is giving wrong thing? I make that assumption. Yeah, I make that assumption. It's like creating those assumptions to explore the space between their satisfaction. Okay. Reinforcement learning. Okay. Reinforcement learning is really about making decision via reinforcement learning. It's a different type of learning. To reinforcement learning, I don't give the traffic signs to tell me what's on the traffic signs. What I'm asking reinforcement learning is, what should I do? So very, very basic stuff. I've got an agent. That agent is making some kind of action in the environment. The environment, in return, is giving some sort of rewards, immediate rewards to the agent, and it's also changing a state of its own and of the agent. The agent then makes an action, collects the reward, changes the state, makes an action, collects reward, changes the state. And this is all driven by the policy. And I'm asking, what kind of policy should I apply to maximize expected rewards over time? So it's a reward-driven system. It's like when you give your dog a treat, every single time the dog is gonna bring back something, it gets a treat. So these treats train the dog to behave better and better and bring you more and more stuff. It is really goal-directed learning from interaction. And we see it also in very many applications. We can do automated vehicle control, for instance, in drone, in continuous space even. We see it in playing games, playing Atari. We see it in AlphaGo. We see it in chatbots. Chatbots is something that can maximize rewards. The reward is how responsive you are or how much stuff you buy that they recommend you, something like this. We can also apply it to medical treatment when we plan a sequence of treatment based on the effect of past treatments. What we are trying to maximize is how well our patients are doing. Here is a bit more concrete example. This is my ego vehicle. I know the ego vehicle is going to make the maneuver going to the left. And what I can control is speed up or slow down, let's say, right? And then I have other participants, that's my environment. I have the pedestrians crossing the street. I have the car going. And I really have limited understanding of how they are going to behave. I can argue a little, but I don't really have a true model of them in my hand. I don't have model of people in my hand. And I'm asking, how should the car speed up or slow down to pass through the intersection safely, but at the same time actually pass through the intersection? So when I'm thinking about the rewards that I should give the car to collect, do you have any ideas what rewards I should be collecting when I'm making actions if I want to maximize the expected reward?
Swedish or Italian?
Huh?
Swedish or Italian reward?
What does it mean?
Swedish would mean
Swedish.
safety.
Oh yeah, Swedish or Italian reward. Okay.
Speed,
Okay. So I won't compromise. I want to check one. Yeah, it's like somewhere in the middle. So what reward? So okay, but those are exactly the two components that should go into the reward. The reward has components, right? So I don't want to hit anything. So what kind of reward should I be giving for hitting a thing or a pedestrian?
Negative.
Like -1,000,000 or something, right? So if I hit a pedestrian or a car, I'm going to collect -1,000,000, and that's going to drive me, when I'm trying to maximize the reward, it's going to drive me not to hit them. But then I want to go through the intersection quickly too. What should I give? How should I design it? How should I design the system to do that? So let's say that I'm controlling the car, I'm making the decision about the car's speed every second. So I'm speeding up or slowing down, speeding up or slowing down. And then I'm driving. I'm driving different distances through my trip.
Short time to distance
Yeah.
to intersection.
Yeah, right? So if I find a reward that is proportional to the time it takes me to the time that it takes me to go through the intersection, that's what I'm after, right? So for instance, I can say that I'm going to give -t for every 100 meters, and t is going to be the time it takes me, right? So when I'm maximizing my rewards, I'm maximizing -t1 plus -t2 plus -t3 and so on. I'm trying to shorten the time that it takes me. But then there is the super high negative reward for hitting stuff. And that's going to prevent me to go fast and hit. Instead, I'm going to go as fast as I can while not hitting. So now we broke some sweat while trying to design those rewards, right? That's one of the challenges of reinforcement learning, is how do you design your rewards? That's something that's up to you guys. If you want to use reinforcement learning, you need to define what's the rewards. What's the rewards that are driving you? Unless you actually have something to observe that can tell you what are the rewards driving that system. So there are also areas called inverse reinforcement learning, where you are trying to learn the rewards by observation. Okay, now reinforcement learning in safety critical systems. Again, TrustWorthy, CPS. So what we are facing is that we designed this reward function that is extremely discouraging hitting the pedestrians, right? And how reinforcement learning works is that I'm going to run tons of simulations of these scenarios, and I'm going to probe which policies are going to give me better results and which policies are going to give me worse results, and I'm going to exploit the results that I'm getting. At the same time, I'm going to explore a little bit around to make sure that I'm not stuck in some kind of local maxima. Right? So I'm going to be exploring, and now I'm saying I'm doing that in simulation, obviously, because in this scenario, I'm not going to let the reinforcement learning algorithm learn by trying and seeing and collecting actually the rewards for hitting pedestrians. I'm going to train it in simulation, and then I'm going to go to the real world and apply a good enough policy that I pre-trained, right? But still, is that going to be safe enough? Did I explore every single possibility that there is? Well, maybe not, because I just have this like massive negative reward, but I may come across a situation that I have never seen before in my life. And again, I actually may accidentally hit pedestrian and learn that that's something I shouldn't have done. So I need to prevent that in safety critical systems. So again, formal methods community thought like this is something we can help with. And there are different kind of efforts working with reinforcement learning towards safety. So by the way, if you Google up safe reinforcement learning survey or overview, you will get maybe a survey paper from a bunch years ago. It's a super nice, safe reinforcement learning paper, but safety there is perceived largely from soft perspective, meaning that you do reinforcement learning, and when you are seeing that things go out of hand, you get a human in the loop who is going to save it all, right? Like that red button on my car, like I'm going to see that I'm going to hit pedestrian, so I'm going to stop. It's got a little bit more of this flavor. So now we are talking about provable safety. So when we are talking about provable safety, we are talking about maybe formal methods. So here's one idea that is from last year from my collaboration with a couple people. We preface the application of actions by model checking. So I take my specification, I take my MDP model of what I know is there. I come up with model checking that is going to tell me whether the action that I'm about to apply is actually safe or not. And if it's a safe action, then I feed it to reinforcement learning agent. I apply that safe action to environment, and then I collect my reward. And again, I know which actions are safe, and I'm only applying those safe actions. So what you can see here is, this is through the time, classical reinforcement learning without the model checking is, having some sort of collision rate around 5%, and then it's getting to 2%, and as it goes, it's improving and improving. What we did is with the safe stuff, for a long while we were not getting really any successful policies, but after a while, meaning that we kind of did not know what to do, but after a while we started off getting policies that had zero collision rate. It took a longer while to train this algorithm, but it was safer from the beginning. So that's one of the trends that the community is looking into, joining sort of reinforcement learning with formal techniques, with formal methods, verification and model checking to keep it provably safe. Yeah? Okay, good. By that, questions? Any questions? Yes?
Okay, we'll scroll back to the previous. So MDP model, what does this model actually? The behavior of the vehicle or?
In the environment, yeah.
Environment.
Yeah, it's Markov decision process, so it's probabilistic, so we assume that we are having some kind of model, some kind of idea. Yeah. So that brings us to question like, do I really need reinforcement learning at all? Cannot I just use these formal methods as an alternative to decision making from the beginning and not to do like any reinforcement learning whatsoever? And this is a question that we ask ourselves outside the context of learning some years ago. So especially in robotics and control, this trend emerged about 10 years ago when we looked at model checking paradigm in context of autonomous systems. So model checking paradigm, roughly, I've got a system and a controller, so some kind of system, and I have a model of it. And then I have a specification, some kind of temporal logic formula typically or something like that. And I'm going to ask a question, do all the model executions satisfy the formula? And then I get the answer, yes, I do, or no, and then you ideally get a counterexample too. So this is model checking, this is what Ed Clark got his Turing Award for, and so on. Very, very classical and old topic. And then when autonomous system came and we started designing controllers for autonomous system, we started asking like, so I'm going to design a controller and then I'm going to ask whether the controller is right. Shouldn't I be actually asking, how do I design controller that is right by design? It's correct by design. So I took my system and I did not have the controller now. I still had my specification and I twisted, not I, but the community twisted the methodology, the model checking methodology to answer instead which of the controllers ensure the satisfaction of the formula. And then you get either a provably satisfying optimal controller, or you get, sorry, there is no such provably satisfying controller. And this really ended up being a twist to the model checking technique. So it all started working very nicely. We started getting provably by design controllers. Excellent. So why do we need this reinforcement learning thing? So what I would like you to take a moment on, maybe like 3 minutes, and maybe discuss in pairs or think alone or something like that. Now that we had like this super fast introduction to reinforcement learning and formal synthesis, which of the things are strong and weak in these aspects? In system modeling, do I need to model a system? How much do I need to model a system? How true does my model need to be able to make some sort of good conclusions? How easy or difficult it is to define a specification? How easy it is to say what I want from my system? Can I handle uncertainty? How well can I handle uncertainty? Do I get any guarantees in that framework on what's coming out? And how computationally tractable it is? Think a little bit, go by your gut feeling, discuss a little, and try to think where these two techniques, the reinforcement learning and the formal synthesis, are strong and weak. 3 minutes go now.
Related field and controls, supervisory controls. They're using synthesis, which I guess is closely related, but yeah, they also have like a discrete event. Late fame is actually from that field. That's nice. I was expecting a Mentimeter here too.
You started a lively discussion. I hope that will continue through the dinner. But now let's try to make a wrap and give space to the autonomy panel. So, system modeling, what did you think? Anyone, just say what you thought. Like, you're looking at me. You want to speak? Yeah? try to see like how do I design a reward for a car going through intersection. Not super easy and not super intuitive. Handling uncertainty. Who is winning there? Reinforcement learning, right? I mean, that has a lot to do with the system modeling, but reinforcement learning that's built to work with MDPs and POMDPs, these formal synthesis techniques, they are techniques for MDPs and POMDPs as well. But a lot of that is rooted again in models that are discrete and that are well defined. Maybe hybrid and continuous if we do the appropriate approximations, but handling uncertainty is a bit better supported in reinforcement learning. Guarantees. Formal methods. That's what formal methods are about. Those are the guarantees. That's where we get our trustworthiness. Computational tractability. Reinforcement learning, for sure, right? Formal methods that are originally based on like full-blown search and theorem proving, and a lot of things are very, very complex there. They are probably going to be able to handle smaller problems than reinforcement learning in the same time. And when we look at that, the strengths and the weaknesses kind of complement each other. So the obvious question that is there, that our community now asks is, how do we get the best of both of the worlds? And that's where I would like to end.
I was just
Mark.
wanting to ask about the specification definition. I guess it depends on how you see it, but I see that in both it's a challenge to get the award or the specs right.
Yes, yes, okay.
So
Yeah.
I'm not sure I see a clear winner in that sense.
Yeah. So Martin is saying that it may be a challenge to get the specification right, both in reinforcement learning and in formal synthesis. Yes, that is true, right? But if you know what you want from your system, getting it to the formalization, how difficult is that? That could be something that I think, I don't know who else, but I personally think that that's where formal methods are winning, because we have we have some interfaces for that. Yeah. Cool. Questions? Not? Then I'm looking forward to seeing you tomorrow morning. Huh?